Hello, class. Gonna wait for the number of concurrent viewers to go into the 20s or so. Good morning if you're just joining. I went for a run yesterday and it was probably the worst run I've ever done in the worst run I've had in the past probably year or so. It was the first time I've run in a week because of the bad air quality. And so I was just excited that the air quality was good, but I didn't realize it was like 100 degrees. And so I went out and I immediately got a stomach cramp, and I had sunscreen on, and the sunscreen was, as I was sweating, the sunscreen was dripping into my eyes, burning my eyes. It was just a miserable experience. I'm going to try it again today. Waiting for a few more viewers. Good morning. I will wait one more minute. Okay, I think I'm going to start. Good morning, everyone. Happy Friday. I want to remind you to submit your daily attendance if you haven't already, and I also want to remind you that you have two quizzes that are due at 11:59 p.m. tonight. So that would be Kinematics Quiz 2 and Kinematics Quiz 3. Those came from last week. Okay, so after this lesson, you should definitely prioritize those if you do not have the grade that you want on those yet. Okay, so I'm going to switch over to the document camera. Today, we are going to be talking about some really useful stuff in physics. And the subject of today's lesson is called uniformly accelerated motion. Okay, and uniformly accelerated motion means that the acceleration is constant. Okay, the acceleration is constant. So in real life, oftentimes the acceleration is constant, but it doesn't have to be constant. So, for example, how could you change the acceleration in real life? If you're in the car and you push the gas pedal down, the car is going to start to accelerate. But what happens if, while the car is accelerating, you push the gas pedal down even further? It's going to now start to accelerate even more. So the acceleration changes when you push the gas pedal down further. What if you were pushing the gas pedal down and you're accelerating, but then you lifted off the gas pedal and you hit the brakes? Your acceleration changed from positive to negative. So those are examples of non-uniformly accelerated motion. But today we're talking about uniformly accelerated motion, okay? So it's kind of the simplest case of accelerated motion. And it applies all over the place. So, for example, gravity, if you drop something, that thing will accelerate uniformly, so it will have a constant acceleration throughout the fall. So I have a question for you, and maybe you could put it into the live chat if you know the answer. What does a velocity time graph look like if it is representing uniformly accelerated motion? Okay, so I'm going to just wait until someone answers that question. Okay. And while I wait for someone to type it in if they know the answer, I want to talk about the meaning of the y-intercept in a velocity time graph. If you talk about the y-intercept, well, the y-intercept is basically the velocity at time 0, okay? Right, because we have time 0 is right here, and this is the velocity at time 0. So this would be the initial velocity, v naught. Very good. Someone answered straight line. Thank you for responding. Excellent. Yeah, so because acceleration is the slope of a velocity time graph, if you have a velocity time graph that just has a consistent slope, that means that the acceleration is constant. So this would be an example, straight line velocity time graph. So that's what we're going to be studying today, a straight line velocity time graph. All right. And so we're gonna get 3 really useful equations. Okay, 3 really useful equations, and then we're gonna practice using those equations. So these equations apply to uniformly accelerated motion. So let me just draw a velocity time graph that would not be uniformly accelerated, just to show you the difference. If you had a velocity time graph that looked like this, see how you have 2 line segments, so you have 2 different slopes, which means you have 2 different accelerations, okay? So the acceleration changes, then that means that you do not have uniformly accelerated motion. Similarly, if the velocity time graph is bent, that means that the slope is changing. So that would also not be uniformly accelerated motion. So it's got to be a straight line. Okay. So we're going to derive 3 really useful equations pertaining to uniformly accelerated motion. So here we go. The first equation comes from y equals mx plus b, which is the equation of a line. Okay, so this is a line, so it has a equation of the form y equals mx plus b, but we are going to convert it into physics language, okay? So, for example, y, we don't have y on the vertical axis. We have another variable. We have v. okay? So we have v final. We do not have x on the horizontal axis. We actually have time. So instead of x, I'm going to write time. All right? M, which in your math class stands for slope, in physics, if you have a velocity time graph, it's not slope. Slope is not m, slope is the acceleration. So I'm going to write a. Okay? And then the y-intercept, b, is just the velocity at time 0. Right? Because if you think about what the y-intercept is, the y-intercept is the y value when x equals 0. Okay? So the intercept here means the velocity value when time equals 0, which is the initial velocity. So this is our first equation. Okay? It's simply expressing the fact that the velocity time graph is a straight line, but it's writing it in terms of different variables. Okay? The second equation is for delta x, the displacement. Okay? So go ahead and type it into the live chat if you know how we can get displacement from this velocity time graph. Okay? And so while I wait for someone to type in the answer to that, I just want to talk about if this graph has a width t, then this line will climb up a distance at. Why is that? That is because if we do rise over run, rise over run is going to be at over t, because the rise is at, the run is t. And the t's cancel out, and you just get rise over run is the acceleration. Okay, so slope is acceleration. So waiting for someone to type in and tell me how to get displacement from a velocity time graph known as, come on, someone type it in. I'm going to wait 10 more seconds. All right, no one wants to type it in. I'm bummed out. So to get displacement from a velocity time graph, you do area under the curve. Okay? So area under the curve. That was the subject of the last lesson. Was, remember, we did area under the curve of velocity time graph to get how far does the thing travel. So if I have this velocity time graph, see how this, I want to calculate this area, this entire area. And I'm going to think about that area as a triangle plus a rectangle. Okay, triangle plus rectangle. So I'm doing this rectangle plus this triangle. Okay, so it's going to be rectangle plus triangle. And they're both above the horizontal axis, so they're both positive. Now, if I look at this rectangle, it has width t, and it has height equal to whatever the y-intercept is. This distance is v naught. So this is a rectangle that is v naught by t. Those are the dimensions of that rectangle. Okay? This triangle has a base, t, and while I was waiting, I discussed how this distance from here to here would be at. It has to be in order to make rise over run equal to acceleration. So this triangle has a height of at. All right. So that's going to allow us to calculate the area of both of these shapes. So for a rectangle, we know that the area is base times height. So we have the base is t, the height is v naught. So you have v naught times t is going to be the area of that rectangle. Okay. And the area of a triangle is 1/2 base height. Okay. The base is t. The height is at. All right. So notice how we have t times t. So that is t squared. Okay. So delta x equals v naught t plus 1/2 a t squared. All right. So that is an equation for delta x. All right. So that gives us 2 out of the 3 equations. So there's equation 1, which is delta x equals v naught t plus 1/2 times a times t squared. Okay. So only the time is squared. So it's like this. Okay. In that. The second equation is this one. V final equals V initial plus AT. Okay? And then there is a third equation that I'm not going to show you how to get, at least unless you come and ask me during office hours, because it's just a lot of algebra, and I don't really think it's that enlightening. But if we take these 2 equations and we mix them together, we get a third equation that is V final squared equals V initial squared plus 2 times the acceleration times the displacement. Okay? So those are these 3 equations are called the kinematics equations. And they're extremely useful. I want to reiterate that these equations will only be true if the acceleration is equal to a constant. Okay? They are not, the acceleration is not always constant, but very often it is. So these are going to be useful pretty much all the time in this class. Okay? All right. One of the things I want you to notice is that each of these equations has 4 variables in it. Okay? 4 different variables. So the first equation, for example, has delta x. It has v naught. It has time. And it has acceleration. And then there's time again, but I'm not going to count it because I already counted it there. So it has 4 distinct variables. Okay? The second equation has 4 distinct variables. V final, V initial, acceleration, and time. All right? The third equation has three variables: v final, v initial, acceleration, and it's almost the same four variables, but this one, instead of having time, has displacement. Okay, so all three of these equations are expressing the fact that it is uniformly accelerated motion. It's constant acceleration. But they're expressing it in different ways. So I want you to think about these three equations sort of like a tool that you can apply to different physics problems, okay? So it's kind of like if you have wrenches, you have different sized wrenches, and you use the wrench that is the correct size to solve your problem, okay? Similarly, I'm going to teach you how to use these equations as a tool, and you will pick the right tool to solve the particular physics problem, okay? So the rest of today's lesson is all about doing examples with these equations, okay? So let's do an example. Let's say a drag racer starts from rest and completes a, let's say, 400-meter long race in 9 seconds. What was the acceleration of the drag racer? Okay, so this is an example of a kinematics problem. I see this a lot because I live in Laverne, kind of right by the racetrack, and actually I oftentimes I go. There's a hill kind of next to the racetrack, and you can go up on top of the hill and you can see the drag racers rather than pay $100 for the ticket. So I do that sometimes because it's really satisfying to hear the drag racer go by and you can like feel it in your chest. Okay, I enjoy that. And when I'm watching, I usually see that the races take about 9 seconds. Okay. So what we want to do is we want to parse the problem. So parse means like scan it for information. So I'm parsing this problem. I'm going for information. Okay. So drag racer. Drag racer starts from rest. Boom. That's our first piece of information. Starts from rest means that you have no velocity to begin with. Okay? So that means that V initial equals 0 meters per second. Okay? Completes a 400-meter long race. 400 meters. Meters, that's a measure of distance. Okay? So this is telling us that delta x is 400 meters. Okay? In 9 seconds. Seconds is a measure of time, so that means time is 9 seconds. Then it says, at the very end, we get to what we're trying to figure out. What was the acceleration of the drag racer? I'm, of course, assuming that the drag racer is accelerating at the same rate for the entire duration of the race, because in order to use the kinematics equations, the acceleration must be constant. So, I want to know what is the acceleration. So I'm going to say acceleration equals question mark. So you can see that we have 4 variables here. Which of the kinematics equation has those 4 variables? 1, 2, 3, or 4? Go ahead and type it into the live chat if you know the answer. 1, 2, 3, or 4. Yes. Excellent. Equation 1. Excellent. So, very good. So I'm going to start with the equation. Delta x equals v naught t plus 1/2 a t squared, because that has all these variables, okay? So now what I'm going to do is I'm going to substitute the numbers in for the variables, okay? So delta x, 400 meters. Initial velocity, 0. Time, 9 seconds. Now, I normally, if this wasn't our very first kinematics problem, I would just write 0 for this and I would forget about it. But I'm just explicitly showing 0 times 9, which is, of course, equal to 0. Plus 1/2 times the acceleration. So acceleration is unknown. That's what I'm trying to solve for. So I'm not going to replace that variable. I'm just going to leave it. And then t squared. That would be 9 squared, which is 81. Okay. So now going to the next line of this, I see 400 equals, now this term is 0, so I'm going to drop it. 81 over 2 is 40.5. All right. So notice how I have turned this into a pretty simple algebraic equation that I can solve for the acceleration, okay? So I just divide both sides by 40.5, so it's going to be roughly 10. 400 divided by 40.5 is an acceleration of 9.9 meters per second squared. Okay? So that solves the problem. Cool. I just want to show you for a second what would happen if you chose the wrong kinematics equation. So the correct kinematics equation, the correct tool for this problem to unlock this problem was the first kinematics equation. But what if I had decided to use the second one? What if I said v final equals v initial plus at? What if I decided to use that one? Well, when I go to substitute in, I would say, okay, v final isn't in this list, so I just leave it as a variable. V initial is 0. Acceleration is unknown, so I leave that one as a variable. Time is 9 seconds. So I would get the equation v final equals 9a. I can't solve that for the acceleration, right? Because I don't know what the final velocity is. So, and then furthermore, I have this extra piece of information that I'm not using. So basically, if you happen to accidentally choose the wrong equation, when you start plugging in numbers, you're going to notice that something is amiss, okay? Let's do another example. Let's suppose a car is cruising at 40 meters per second. That's pretty fast. That's about 90 miles per hour. Okay. Driver sees a deer. All right. And slams on the brakes. Decelerating at, let's say, 25 meters per second squared. So quite a strong deceleration. Okay. And we'll say coming to a stop. So as you know, when you're going fast and you hit the brakes, you don't stop instantly. You actually are rolling forward while you're stopping. This is why you know, if you're in driver's ed or you have your driver's license, you know that you always leave a space between you and the car in front of you, so that you have enough distance to roll forward and stop if they stop suddenly. Okay, and the faster you go, the more space you need in order to safely stop. So, you know, for example, you can be closer to the car in front of you going down Indian Hill Boulevard than you could be if you are going on the freeway. Okay? So, what I would like to know is how far does the car roll forward while stopping? Okay? So we're going to go through and we're going to parse the problem to try and find the information, this list of the known variables. Okay? So first of all, we say the car is cruising at 40 meters per second. That was what its speed was before the braking began. So that means that V initial is 40 meters per second. Okay. The driver sees the deer and then slams on the brakes, decelerating at 25 meters per second squared. So the acceleration has to be negative because the car is slowing down. If the acceleration was positive, the velocity would go from 40 to 65 to, to 90, and it would just keep increasing. So the fact that it says decelerating means we have to kind of put in the sign of the acceleration by hand at 25 meters per second squared. So the acceleration is negative 25 meters per second squared. And it says that the car comes to a stop. Okay? Coming to a stop means your velocity is 0. It's at the end of this period of deceleration, so that means the final velocity is 0. And we want to know how far does the car roll forward while stopping. That is delta x. So delta x is the question mark here. So we have 4 variables. Which kinematics equation has the right stuff? I will wait. Excellent. People are typing in 3. That's very good. The third equation is the right equation. So, V final squared equals V initial squared plus 2a delta x. V final is 0. So now what I want to do is I want to put the numbers into this equation. 0. V initial is 40 plus 2 times negative 25 times delta x. Simplify. 0. 40 squared is 1600. 2 times negative 25 is negative 50. So we solve this equation for delta x, and we're going to get that delta x equals 1600 over 50, which is going to be what was that, 320 meters. That doesn't sound right to me. Or 32, my bad. 32 meters to stop. It's about 100 feet. Okay? So what if the deer was 30 meters in front of the car? Then that would mean that the deer got splattered, right? Because the car rolled forward 32 meters, but hit the deer with 2 meters left to go. All right, so that would be bad for the deer. Maybe it wouldn't be splattered, because what's happening as you're rolling forward is you're slowing down. So because it was so close to the end, it had almost stopped. It might have just been a gentle tap, and the deer might have survived. So if the deer was 40 meters away, then there would be no contact between the deer and the car. All right. We will do one more example and then transition over to the Zoom room. A rocket can accelerate at 30 meters per second squared. Okay. The rocket increases its velocity from 1,000 meters per second to 2,200 meters per second. Okay? How long, or how much time, I'll be more specific, how much time must the thrusters be fired for? Okay? So this is a fairly realistic problem. Anyone ever played the video game Kerbal Space Program? It's an excellent, 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 excellent game to teach you about physics if you have not played it. If you have a computer and you like to play games, I would highly recommend playing Kerbal Space Program. I will type it into the chat. Now, one of the things that you do in Kerbal Space Program is you can build rockets, and then you can launch them, and you can see what happens, basically. You can steer the rockets around. It's basically a sandbox engineering game. So what you do in Kerbal Space Program is your space probe is orbiting the Earth, for example, and then you want to make the space probe go faster, so you push a button, and then the thrusters start firing. And the more time you fire the thrusters for, the more speed the probe will build up. Okay? So you need to have a certain amount of speed in order to, for example, leave the planet and travel to another planet. Okay? So one of the things you have to do is you have to fire the thrusters for the correct amount of time. Okay? That's very realistic. In NASA, they calculate how much time do the thrusters have to be fired for to achieve this velocity, okay? And then they program, the thrusters are controlled by computers, and then they program that into the computer, and everything works out fine. So what information do we have here? We have that the acceleration is 30 meters per second squared. Okay, let's zoom in a little bit. Acceleration is 30 meters per second squared. The initial velocity is 1,000 meters per second. The final velocity is 2,200 meters per second. And we want to know the time. All right. So, as you could guess, I gave us one example for each of the kinematics equations. So this one is V final equals V initial plus AT. V final is 2200. V initial is 1000. Acceleration is 30. And time is unknown. So we solve that equation and we get the time is 40 seconds. Okay? So that is my lesson for today. So I will meet you in the Zoom room in just a moment. Okay? See you soon.